Hello, welcome to a new video. In this video, we are going to discuss about two important graphs. These graphs are called the forbidden graphs in the area of, and these graphs are used in the area of planarity in graph theory. What is the importance of the graph is that if the two graphs K5 and K33, and these are called the forbidden graphs. K5 is the complete graph on 5 vertices, and K33 is the complete graph containing 3 vertices each in its bipartition. There are two important results. These both results finally take us to the same conclusion, but the statements are slightly different. Let's state the first result. A finite graph is planar if and only if a finite graph is planar if and only if it does not contain a subgraph that is a subdivision of the complete graph. If and only if it does not contain a subgraph that is a subdivision of the complete graph K5 or the complete bipartite graph K33. So this is the first result. So that helps us to test the planarity of a given finite graph. Similarly, we have another result. A finite graph is planar. Another important result that states that a finite graph is planar if and only if it does not have K5 or K33 as its minor. So you need to know two related concepts, two concepts in graph theory to understand the two results, or to make a clear understanding of the these two results that we discuss here. First concept is the subdivision of a subdivision graph of a graph, and the next concept is the minor. So what's meant by the subdivision? Subdivision in graph theory, two graphs G and G dash are homeomorphic. If there is a graph isomorphism, if there is a graph isomorphism from some subdivision of G to some subdivision of G dash, G or G prime. See, the two graphs, we consider two graphs G and G prime, and we say that they are homeomorphic. The two graphs are homeomorphic if there is a graph isomorphism from this is not isomorphism exactly. It's a different concept, homeomorphism. So see, if we can define an isomorphism from the subdivision of some subdivision of the first graph G to some subdivision of the second graph G prime. If the edges of a graph are thought of as lines, if the edges of a graph are thought of as lines drawn from one vertex to another, then two graphs are homeomorphic to each other if in the graph and that it goes like let's take that incomplete. Let's take the complete definition of subdivision. Homeomorphism actually is explained here. So a graph two groups are homeomorphic if there is a graph isomorphism. If there is a graph isomorphism from some subdivision of G to some subdivision of G prime. If the edges of the graph are thought of as lines drawn from one vertex to another, as they are usually depicted in illustrations, then two graphs are homomorphic to each other in the graph theoretic sense. precisely if they are homeomorphic in the sense in which the term is used in topology. Here we use the topological sense of homeomorphism. The topological sense of homeomorphism is used to define the homeomorphism, the concept of homeomorphism. So we don't want to go into the details of that concept. In order to complete that definition, I have directed you to the definition of homeomorphism. So we are going to close it, and we will come back. See, that subdivision, that concept of subdivision is important. And we can see some examples later. But in the second case, now to understand that minor, the concept of minor is is required to know about the second result. What's meant by minor in graph theory? An undirected graph H is called a minor of a graph G. An undirected graph H is called a minor of the graph G. If H can be formed from G, by deleting edges and vertices, and by contracting the edges. See, there are two operations suggested here by deleting vertices and edges. See, if we delete vertices, edges and vertices, first we delete, suppose we delete some vertices and edges, and then and after that, by contracting the edges, some edges can be contracted, and this way, if we apply this operation, then after applying this operation, we get a new graph, suppose, then that graph can be called the minor of the given graph. Okay, and that minor operation can be seen here. It is explained here. See this animation here. You can see. Initially, you can see this is the Peterson's graph, and then in the Peterson graph, one vertex and the three edges joined to that is removed. So one vertex and three edges are removed. After that, you can once again see this vertex, ninth vertex will be removed, and the three edges will be removed. After that, this vertex, now the one edge is contracted to it, is then joined to there are three edges which are then joined to the adjacent. See once again. Now this vertex, it is then joined to that vertex here, then that vertex joined, and this vertex also joined to that. After that, we rearrange the position of the vertices actually, then that means we are taking an isomorphic redrawing of isomorphic drawing of the final graph, and then we get a complete graph, bipartite graph. So you can again look at that animation. See, this vertex and three edges will be first removed. Okay, then this vertex is then joined to that vertex, this vertex, but the edge connections are there, preserving the edge connection. No, the three vertices were then joined. So as a result, the one edge is then deleted. It is not deleted. It comes disappearing there. It is disappearing. That edge is then disappearing as this vertex joined to that vertex. So okay, then and hence we get this graph. The last graph is thus a minor of this graph. Therefore, you can say that K33 is a minor. That is the last graph which we obtained, is a minor of the Peterson graph. Peterson graph is the original graph. See, this is the Peterson graph. Okay, so this is the process of obtaining minor of the Peterson graph. So see here, you can look at it again, patch it again, and then okay, we are obtaining the minor. Okay, this is the concept of minor. Then if we have a minor, therefore this illustration says that, or this animation says that Peterson graph is not a planar graph, because that forbidden graph is there. We obtained the forbidden graph K33. We obtained the forbidden graph K33 as a minor of the Peterson graph. Therefore, according to the second result, a finite graph G is planar if is planar if and only if it does not have K5 or K33. K5 or K33 as a minor. But you know, in this case, in the case of the Peterson graph, we can obtain K33 as its minor by using the minor operations. By applying the operations for minor, for making minor, we can convert the given graph, the Peterson graph, into the complete graph on 6 vertices, that is the complete bipartite graph K33. Okay, so that is not a planar graph. So that is these are the two important results in and one more important thing we want to say about the first result is that this result is due to this Kuratowski, and he was the mathematician who proposed this result. Kuratowski, he was a Polish mathematician and a logician. He was one of the leading representative of the Warsaw School of Mathematics. Okay, then the second result was due to another mathematician, Wagner's theorem. See, this was the second result was due to Wagner, and so it is known as the Wagner's theorem, in which that minor concept is used. Okay, thus we have in this video we have discussed the two important results that will help us to say whether a given simple graph is planar or not planar. And both the results gives us a characterization of planar graphs, but the first result you can see the concept of subdivision graph is used, but in the second result the concept of minor is used. And but in both graph you can see that very interesting thing that the forbidden graphs, the first forbidden graph is for K5 and the second forbidden graph is K33. See, both the forbidden graphs are equally used in both graphs. So that is the important. So these are the similarities and differences of the two results. First theorem is known after Kuratowski, and the second theorem is known as Wagner. Okay, thank you.